All right, today we are looking at valid or validate binary search tree. This is day 31. We are just about at a month of NeetCode. Super exciting. And we're approaching the halfway mark. Also very exciting. But let's take a look. So this is, once again, we have moved on from just binary trees to now binary search trees. I think, again, you're more commonly asked binary search tree questions just because there tends to be a little bit more like reasoning to get to the solution. And they've just added these company tags, which is very interesting. I think what this means is that maybe this question has been asked by these companies. Could be wrong here, not 100%. I'll maybe explore that more. She does bloom on my berg. I completely agree. All right, but let's take a look here. Yeah, we'll read through the prompt. We'll do a little diagramming as usual, and then we'll see if we can throw a solution at it. So given the root of a binary tree, we want to return true if it is a valid binary search tree, and otherwise we want to return false. And we've already talked about this, but just for a reminder, a valid binary search tree satisfies the following constraints. The left subtree of every node contains only nodes with keys less than the node's keys. The node's key, rather. The right subtree of every node contains only nodes with keys greater than the node's key. And both the left and the right subtrees are themselves binary trees. So what this means is that everything to the left of a node will have smaller values, everything to the right of a node will have larger values, and this is true for every node in the tree. Which actually is going to be super useful in terms of the logic for this problem. So this guy, 213, is a valid binary search tree, and this is because for this node, everything on the left, which is just one node, is smaller, and everything on the right, which is just one node, is bigger. And then when we get down to here, the none nodes just have no values, so we do not need to kind of evaluate them. Okay, by contrast, this one, the left child of the root is bigger than the root, which is not how binary search trees work, so this one fails actually immediately. Okay, and they don't give any examples, so we'll do like a multi-leveled or a 3+ leveled tree in just a sec, because there's some additional considerations to take the further we move down the tree. Yeah, again, they're giving us this list-looking thing as a way to represent the tree rather than drawing it for us, but it is where we are going to be given just this one node at the top, and we'll have to follow pointers to traverse the tree. All right, so finally some constraints. The number of nodes in the tree will be between 1 and 1,000, so there will never be no nodes, although that wouldn't be super tough to handle. And then the values will be between -1,000 and 1,000. This time, actually, for the first time, that's kind of important because we are going to do some comparisons, and if it was possible for these to reach like the integer overflow limits, then that might be concerning to us. But they're very manageable, very reasonable, so we don't have to worry about that here. Yeah, speaking of which, integer overflow limits. Discussing integer overflow limits with Neil today? My life is made. I can die in peace. Anyways, if you have any questions about the prompt here, let me know, but otherwise we'll explore one more example that is a little bit more in-depth and then talk about how we can code this up. Let me think about... We'll make this work for the first few levels, and then we'll kind of blow it up at the bottom here. Okay, so let's say this is 6. Let's say this one over here is, yeah, I said what I said. And let's say this guy is maybe 9. And then we'll keep going. Maybe this one will have like a 5. Okay. That's gonna bug me. Oh, did they change how the fill works? That's so sad. Why would they make it worse? Okay, anyways, let me draw the bubble first. That's not a bubble. Okay, I'm spending too much time on this. This is not the important part. Okay, maybe we got a 5 here, and then over here, so valid, completely valid so far. Hopefully you're following that. Maybe this one can be a... Ooh, actually, let's make this one a 4. Okay, and then we'll just add one more child here just for the sake of making this a little bit less symmetrical looking. And we'll maybe make this one a 10. Okay, so here's our example tree. Let's actually start by thinking about what it would look like to insert a node to this tree. That's obviously not the problem, but I think this is instructive about like where in fact, you know what, I'll erase this and then I'll put it in the wrong place. So let's say we wanted to add the node 5, or a node with value 4. Take that back, a node with value 4. What we're going to do is we're going to start at the root and figure out which half or which subtree we should put the node into. So if we start at 6 and we're trying to add the node 4, we're first going to compare it against the root's value, and if it's smaller, we'll go left, and if it's bigger, we'll go right. So the first step here, or the first kind of move that we're going to make, is we're going to go this way, right? And we're going to repeat this question for each of the subtrees until we find an appropriate place for this node. So if the node that is currently the root that we're looking at is 3, well, 4 has a larger value than that, so that tells us that the position of this node should be somewhere over here. And once again, we look at the 5, we ask, hey, is the node we're adding smaller or larger? Well, in this case, it's smaller, so we go this way. And now that there's nowhere else for us to go, this would confirm to us that the correct place for the 4 is going to be over here. So if we needed to insert the node, that's what it would look like. Okay, and in fact, I'll even just leave it there. Okay, so there's a specific path that we're going to follow, and at each of the stops, we ask ourselves, which direction should we go to find the appropriate place for this node? Okay. Now, if I wish I had not chosen these numbers. I'm going to change the root to 7 real quick, which doesn't change the structure. But what I'm also going to do is I'm going to add the node 6 over here. Okay, because I actually want us to go over a failure example real quick. Okay, so let's say this was the structure of our tree. How could we know if everything was or wasn't in the appropriate places? I didn't even realize. It's so funny. The root is 7, and I've just added in this 6 node just for the sake of demonstrating how we can check this logic. Okay, so if you think about how we inserted that 4 node, it's a series of decisions that that kind of have to lead into each other, right? So in order to get to this point, we are going to have to follow a path that tells us, hey, that this number is less than 7, but greater than 3, but less. So in fact, let me write these down on a number line here, because I think this is going to be helpful to visualize it. What we're saying in the first decision is, hey, we have to be somewhere less than 7. And then the second decision we make says, hey, we have to be somewhere greater than 3. And then the next time we do this, we say, hey, we have to be actually less than 5. And that's when we make the decision, right? So notice a few of these specifiers here are redundant, right? Specifically, if we need to be less than 7 and we need to be less than 5, well, it doesn't matter. Like, we don't need the less than 7 specification anymore. If we have to be less than 5, we can kind of begin to ignore this. Or to be more specific here, since we're getting to more specific numbers the further down we go in the tree, every step that we take, every direction that we go in the tree is going to change either the maximum value if we go to the left, because we have to, we're choosing a smaller number, or it's going to change the minimum value that would be valid if we go to the right. So when we take this first step, what we're saying is we must be looking at a number that's less than 7. We must be looking at a number that's greater than 3. We must be looking at a number that's less than 5. And we can kind of begin to override either the maximum possible value while still being valid or the minimum possible value while still being valid. Right? And if we kept going, like nobody said it had to be integers in this case. Maybe if we found like or we were trying to insert 2, right? And that in that case we would once again say, hey, it doesn't matter that we needed to be less than 5 before. Now we need to make sure that we are less than 4, right? Well, in fact, 2 wouldn't even go here. Well, actually, this is sort of a good demonstration on why 2 doesn't belong here, because one of the conditions of being on this path is that it must be a number greater than 3, right? So something that could belong here is 3.5, but if we were trying to insert 2, we wouldn't have gone down this path in the first place. And actually, that sort of is the whole gist of the problem. So let's now try this again with a different node. Let's check. Just for the sake of time, we'll skip ahead to this because we already figured out how to figure out if something is valid. But let's try out this 6 node right here. The fact that it is in this position suggests to us that it has to be bigger than 7 and smaller than 9. Right? And obviously 6 is not bigger than 7, although it is smaller than 9. So it's not sufficient that we just look directly at the parent. It's also important that we consider everything else that came in the path before it. Right? Those all still have a bearing on the ultimate decision. It's just that we kind of improve how specific we're being, or we add more specific rules the further we go down the tree. Or maybe we don't. If we just keep going right forever, then all we're doing is all we need to make sure of is that the number gets bigger, 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 right? So anyways, all this to say, if we go left, that adds a constraint that it must be smaller than the number we came from. And if we go right, it adds the constraint that whatever we're looking at has to be bigger than the number we came from. And so on and so forth down the tree until we find an even bigger thing, potentially, or an even smaller thing. Yeah, well, we do, that's a great point, Mince. We do, in fact, exist in the context of all that came before us. And that's exactly the point of the problem. So great point there. Love that. Yeah, okay, so as we go, basically what we can do is we can continue to pass along new information that says, hey, well, since we've gone down this path of the tree, that tells us we have to be within this more narrow range, right? And if that number is not within the range that we provide, then we can say, hey, something went wrong here. This node is not in a valid position, and we can return false. Otherwise, we look through the whole tree and confirm that everything follows the rules that we set forth. And if everything does that, we can return true. So this is very much and logic, right? We need all of the conditions to hold, and if any one of them fails, we'll return false. Okay, and then as usual, we're going to be doing this recursively. And this means that if we get to a none node, it's just sort of like, yeah, we're done. There's nothing to compare here. We don't have to worry about it. There's a few ways to check that. You can say either like when we get to a none node, let's return, or we can say, hey, when we have no children on either side, then we can return. So I'm not 100% sure which one I'll go with yet, but my hunch is it's the none node. Okay, so let me know if y'all have any questions, but we're going to tackle the code now. And the first thing I'm thinking about is there's not a great way to, like, I would like the recursion to handle what the proper range is for each call. So rather than doing this as like global or static variables, I'll go ahead and define a helper in here where we can specify like not only the route that we want to pass, but also, I'll say the lower bound and the upper bound. Ooh, and I kind of hate that I haven't. Okay, I'm gonna match their styling convention here. Okay, so that's the primary thing that we need to do. And all we're gonna do is return, like we're gonna call the function. Now, the root itself can be anything. It doesn't really matter, like we don't need to enforce any boundaries on it. So we can say, oh, sorry, is valid BST helper. So we'll call the helper function. We'll provide the same root, but the lower bound, we can either use the boundaries they gave us. So the problem specified like all the values will be between -1,000 and 1,000. So we could say like -1,001, +1,001. Or for a more generally working solution, we can pass, I I don't know if we've done this before, but float negative inf right here is going to say basically past negative infinity. Just this is always going to be smaller than anything we compare it to. And then float inf here is going to be larger than anything we compare it to. So we don't have to do that because we've been given constraints in the problem, but this is a nice way to make it work in general. Okay, so for any particular node, there's two kind of base cases. So one of them would be if there's no root. In that case, we can actually return true because it's not failed anything, so to speak. Okay, and this is the first thing we want to check so that we don't inadvertently like try to access a left or a right value of none, right? So if not root, we'll return true. Here's the other base case condition that we covered in the example. If the root value is less than the lower bound, or the root value is greater than the upper bound, in that case, we can actually return false because we know that we've found a node that's not in the right position, right? And I think we do want strictly less than greater than. Let me see if they, yeah, key's less than, strictly less than the node's key. Okay, so assuming that we actually got to a node and that node itself was valid, we also need to determine if the left subtree and the right subtree are valid, right? So now we can return, so ask the same question, hey, is the tree valid for root.left? Okay, and actually this is gonna be pretty like long-winded, so I'm gonna go ahead and put this on 2 lines. So root.left, so we're gonna go to the left subtree. If we go to the left subtree, then now whatever we were looking at in the current root is the biggest possible value, right? Everything in the left subtree has to be smaller, but it can also be, like the numbers can go as low as we want, right? Barring like a different condition like earlier in the tree. So we'll pass root.left. The lower bound is just gonna be the same as before, but the upper bound is now the root's value. Right, and so all we're saying here is if we're in the left subtree, the nodes have to be smaller than the root, right? Okay, so that, and we need to meet the condition that for the right subtree, root.right, now the right subtree has the root's value as its lower bound, and whatever the upper bound was before, it's still that. And I think that might be it, which is kind of crazy. I thought that was going to take a lot longer to code. But this is just fundamentally asking the question, like, is the root appropriate? If the root's appropriate, is the left subtree appropriate? And is the right subtree appropriate or valid, right? And we can determine that because we know that the root is going to play a part in the rest of the subtree, right? It's going to act as a boundary. Maybe that boundary will be overridden by, you know, future conditions that we add to the traversal, but you know, we can let those recursive calls handle themselves. Okay, before I start tooting my own horn, let's run it and see if it actually works. Yay! Ah. Oh, we outputted true? Wait, didn't we do... Oh, haha, less than or equal. So I said strictly less than, but if it's less than or equal, we still want to fail, right, if it's equal. Great, and that's that. Yeah. There are probably ways to do this breadth first, but they probably suck, so we're not going to do that. And yeah. So yeah, pretty fundamental to binary search trees, right? The whole shtick is that the condition holds, or the invariant holds for every node in the tree. So we literally just do that. We ask the question for every node in the tree. We just have to modify the boundaries as we traverse. Maybe I need to modify my boundaries to protect myself. Okay, any questions at all? Yeah, so I would say the float inf is a great tool, and assuming we don't have constraints on the problem, for Python at least, this is a great way to do it. Um, for other programming languages that have like integer boundaries, for example, you might like C++ has like max int as a constant, for example. That might be a good way to do it because if it passes that number, then we're experiencing overflow anyways, and that's a problem. Or it's not possible, I should say, to exceed max int, right? Um, so for Python, I would say float inf, float negative inf is probably like a good practice if you are not, given constraints. But well, I guess just to demonstrate, if we pass these numbers because they follow the constraints of the problem, then it should still work. Yeah. So up to you, really. I think it's like it just depends on your use case, right? For something like a LeetCode problem where you're given the constraints, well, you can use them if you'd like, but it might be a good practice to just have float inf in the back of your pocket. There's definitely lots of problems that don't have constraints like that for values, so it can be great just for like a catch-all. Hey, I just need something that's always smaller, or I need something that's always bigger, right? So yeah, and that's that. I think that's all I got for y'all today. It's a great problem. I think it feels real simple once you've kind of like explored how it works. Um, and I think it's quite rewarding to solve. It's very like kind of demonstrates your knowledge of what makes these data structures tick. Great, but we're gonna call it there. I'm gonna go get some pho. I hope you guys have a great night, and we will. I think actually we're not gonna pick it up tomorrow because it's Veterans Day. So I will not see you guys tomorrow, nor will we have a general body meeting. So, anyways, have a good night, y'all, and see you Wednesday.